Okay, so today we're going to go over section 9.3 and we're going to work on the integral test and p-series. So in the last section we defined what an infinite series is, and we defined what it means for it to converge. And we were able it was a telescoping series. We either had a telescoping series and we had a closed form formula for the nth partial sum, so we were able to take the limit and calculate what the series converged to, or we had a geometric series and we had a formula for the geometric series. So in either case we were able to figure out what it converged to. We can't always do this, and so in the next couple sections we're going to just be concerned with trying to determine whether a series converges or diverges. And so we're going to go through some tests. In this section we have the integral test. And so the integral test says if f is positive, continuous, and decreasing for x is bigger than or equal to 1, and a sub n is equal to f of n, then the series and the improper integral either both converge or both diverge. So all this is saying is that the terms of your series are the same as the outputs for your function. We've already talked about when functions converge on an improper integral. We've done that, and what this tells us is that they either both converge or both diverge. Now we're not going to go through a formal proof of this, but I would like to walk you through this a little bit, trying to understand it a little bit better. And so notice that we need the function to be decreasing. Both of these examples here, we have the function that is decreasing. And if it turns out that your that your improper integral converges, and remember that represented the area under the curve of the function, extending the interval forever to the right. Now, so since we're getting the area under the curve, when we're adding up the sequence, because the width of each rectangle here is 1, when we're adding up the series, what we are getting is just the area under the rectangles. And you can see that the area under the rectangles is going to be less than the area under the curve. So if the bigger area converges to a number, then this smaller area should also converge to a number. We don't know what number that is. We can't really tell. And so we're just going to be able to tell whether it converges or diverges. Likewise, if you have a diverging series, since all your terms are positive, as you move to the right, your area is growing and growing, and if it diverges, then the only thing that could possibly be going on is that your area is increasing without bound. But if we use the left endpoint for the rectangles, then you can see that there is more area under the rectangles than under the curve. And so then if the area under the curve is infinite, the area under the rectangles should also be infinite. And so your series should also diverge. Okay, so we have our first problem here in exercises 3 through 22. Confirm that the integral test can be applied to the series, then use the integral test to determine the convergence or divergence of the series. If I tell you how to do the problem, I expect you to do the problem that way. This problem, you can see, is a geometric series, and the common ratio is 1/3. So not only do we know that this converges, we know what it converges to because it's a geometric series, but we're being asked to use the integral test. So again, first we could look at f of x is equal to, and we can write it as 1/3 to the x. And then from our work in pre-calc, we should know this is an exponential function, and that is positive, continuous, and decreasing. So don't need you to do too much here, because this is a familiar function, or should be a familiar function. So by writing it like this, exponential function with a base of 1/3, positive, decreasing, and continuous. So we can apply the integral test. not that comfortable with antiderivatives with exponential functions whose base is not e. So what we're going to do to help us with that is we're going to rewrite this function as we're going to natural log the 3 to the negative x, and then we will exponentiate to undo that. The whole point of natural logging is that allows me to take this exponent and bring it down, and then we end up with e to the negative x times the natural log of 3. Now this is just the composition. This is just a constant composition of a constant times x, e to that. And so then we can integrate this and differentiate it as we need to. Okay, so now we apply the integral test. So we want to find the improper integral from from 1 to infinity of e to the negative x natural log of 3 dx. And again, the way we do that is by replacing the infinity with b and taking the limit as b moves on to positive infinity of the definite integral from 1 to b e to the negative x natural log of 3. Now, if you wanted to use a u substitution and let u be negative x to the times the natural log of 3, you can do that. But this is simple enough to find an antiderivative for without that. This is just like integrating e to the 5x. If it was e to the 5x, you would say that the antiderivative would be e to the 5x, except here it's not, negative x natural log of 3. And then you divide by the 5, but here it's a negative natural log of 3. So you have a factor of 1 over the negative natural log of 3. And we're still taking the limit as b goes off to infinity. We can bring this constant outside, and we're evaluating this from 1 to b. So then we still have the 1 over the negative natural log of 3. And when we put in, we're still taking the limit as b goes off to infinity. And we still have, so now then we plug that in and we get e to the negative b natural log of 3. I'm sorry, natural log of b. Sorry, no, that is right, natural log of 3. Let me clear that out of there. Minus, and when we put in the 1, we get e to the negative natural log of 3. And so then we still have the 1 over the negative natural log of 3, and then we have, we don't really care what the answer is, we just care that it converges. And so this right here, the exponent goes to negative infinity because b is going to positive infinity, and as your exponent goes to negative infinity, e to the goes to 0, and so then what you end up is a 1 over the negative natural log of 3 times negative e to the negative natural log of 3. And so then that is going to be a positive number, and it's going to be finite, so therefore converges. And therefore your series also converges. Again, easier to just notice that that is a geometric series, but you were told how to do the problem, so you had no choice. Okay, moving on to our next problem, problem number 8. Now we have this series, and the corresponding function is f of x will equal x e to the negative x over 2. Clearly this function is positive. We're only putting in positive values for x. So this is positive, this is always positive, so that's positive. Clearly it is continuous, but what is not clear is that this is a decreasing function. And so what will show us that this is a decreasing function is by finding the first derivative. F prime of x is equal to, this is a product, so we have to apply the product rule. The derivative of the first factor is 1. The second factor gets left alone, so you get negative x over 2. And then plus, leave the x alone, and then multiply by the derivative of the second factor. And so you get e to the negative x over 2. This is a composition, so we use the chain rule. The derivative of e to the is e to the, same inside, times the derivative of the inside, and negative x over 2, that's just a linear function, and we get a derivative of negative 1/2. Okay, so we can then factor out the e to the negative x over 2, which then will give us e to the negative x over 2, and then we have 1 minus x over 2. So you can see that this expression here will always be positive. We don't have to worry about that. So to find the sign chart for this, we just look at this expression here. And so for that expression, so we're looking at the sign chart for the first derivative, so that will tell us when it's increasing and decreasing. And so then if I want 1 minus x over 2 to be 0, I have to put in 2 for x. You could set that equal to 0 and solve, or you can just look at it. 2 over 2 is 1. 1 minus 1 is 0. This is just a line. This is the only place that it's 0. It's a line that goes down. So to the right, it's positive. I'm sorry, to the left, it's positive, and to the right, it is negative. So that means that this function is decreasing after 2. Now, the integral test required that our function always be decreasing, and what the first derivative test tells us is that it's eventually decreasing. And it should make sense that the first couple terms shouldn't matter. The first million terms shouldn't matter. It's just that as long as eventually it starts decreasing only, then that's what should matter. And so this eventually decreases after 2. So after 2, it's always going to be decreasing. So we can apply the integral test. Okay, so to apply the integral test, we find the improper integral from 1 to to 1 to infinity of x e to the negative x over 2. Dx. We're going to replace this with the limit as b goes off to infinity of the definite integral from 1 to b of x e to the negative x over 2 dx. Now, to find an antiderivative for this, first thing you might think is u sub, but the inside function is here, and the derivative is of this is negative 1/2, and we've got this extra x here, so that's not going to work. So what we have here is a product, and so then since we can't do this with a u sub, then we're going to have to use integration by parts, right? And so again, should make sense that u should equal x, and dv should equal e to the negative x over 2 dx, right? And so then du will be dx, and v will equal the antiderivative of this is again e to the negative x over 2 times the negative 2. And there we go. When I take the derivative of this, the derivative of e to the negative x over 2 is e to the negative x over 2 times the derivative of the inside, but the inside will give us a derivative of negative 1/2 times this negative 2. We'll get back to here. So then following the integration by parts formula, we end up with the limit as b goes off to infinity of uv negative 2x e to the negative x over 2 minus, but because of this minus, we're going to end up with a plus, the integral of v, so the 2 can come out, and the v du, and du is dx. So then dx, I'm sorry, go ahead and get rid of this. Plus 2 times the integral of v du will just be e to the negative x over 2 dx, which is then again the limit as b goes off to infinity of negative 2x e to the negative x over 2 minus 4 e to the, because we're going to find the antiderivative of this, and we've already done that. We get this minus 2, and so since we had this plus 2, that's why that becomes minus 4 e to the negative x over 2. And then we're going to evaluate all of this formula from 1 to b. So I forgot my definite integrals, my limits of integration here. This should go from 1 to b. Okay. And so then we now have the limit as b goes off to infinity of negative 2b over e to the b over 2 minus 4 over e to the negative b over 2, and then minus what you get when you plug in 1. And when you plug in 1, you get negative 2 minus 4 again minus what you get when you plug in 1. And when we plug in 1, we get minus 2 e to the negative 1/2 minus 4 e to the negative 1/2. To take the limit as b goes off to infinity, this will go to 0 because the numerator is fixed at 4, and that should be a positive because I brought it down to the bottom. And this just increases without bound. Here you have infinity over infinity, so you could L'Hopital it, and if you L'Hopital it, you still have you'll have a negative 2 up on top, and then you'll still have e to the b over 2 on the bottom. So using L'Hopital, which I don't want to do, this will also go to 0. And so then this is a fixed number, and so then your limit is just that number. And so these are like terms. So this is 6 e to the negative 1/2. And so that's what that equals. Therefore, this series converges. I'm sorry, this integral converges. And then therefore, the series converges by the integral test. So again, here we're being asked to do the same thing to determine, use the integral test to determine if the series converges or diverges. The only difference here is we're not given the series in summation notation, so we have to come up with that on our own. So we'll start our series at n equals 1, and the ... means this goes on forever. Otherwise, it wouldn't make sense to talk about convergence. It would be finite because we'd have a finite number of terms. If you look at the numerator, 1, 2, 3, 4, 5, that's fairly easy. That's just n. n is 1, you get 1, n is 2, you get 2. Now on the denominator, 4, 7, 12, first we go up by 3, but then we go up by 5, and then we go up by 7, and then we go up by 9, right? So I showed you that that's what the squares do, but this is obviously not the squares, because 1 squared is 1, and we get 4. 2 squared is 4, and we get 7. 3 squared is 9, and we get 12. But it looks like if we just add 3 to the squares, we will be fine. Okay. So then, again, our corresponding function, f of x, would just be x over x squared plus 3. This is a rational function. Clearly, this is positive because we're only putting in 1, 2, 3. There's no place for a negative to come in to come out of any of this. Clearly, this is continuous because it's a rational function, and the domain is all real numbers because nothing makes the denominator 0. It's just not entirely obvious that this is decreasing. So to show that this is decreasing, again, we could use the derivative. We could find the first derivative. And so then this is a quotient, so we use the quotient rule. The derivative of the numerator is 1, top left alone, x squared plus 3, minus, leave the top alone, x, and we multiply by the derivative of the bottom, which is 6x. All over the bottom squared, which is x squared plus 3 squared. Now, what we get is x squared minus 6x squared, which is minus 5x squared. Plus 3. And then on the denominator, we get x squared plus 3 squared. Okay. Now, x squared, since we're only using 1, 2, 3, is clearly bigger than 1. So then once you multiply it by negative 5, this is obviously less than negative 5. So, and then when you add that negative number with this plus 3, you're obviously going to be less than 0. And so then this is decreasing when x is bigger than or equal to 1. Okay. And so now we can apply the integral test. The integral test here, we're going to take the integral from n equals, So again, we're going to take the limit as b goes to infinity from 1 to b of x over x squared plus 3 dx. This one you should recognize that you can do a u substitution. No need to use partial fraction decomposition or anything like that. The simplest technique is best, and u is x squared plus 3, and then du is 2x dx. We solve for what we have. We have x dx, so then x dx can be replaced with du over 2, and so then this improper integral becomes the limit as b goes off to infinity of, and so then the x dx becomes du over 2. We bring the 1/2 out. U is x squared plus 3, so 1 squared is 4. 1 squared is 1 plus 3 is 4. Change our limits of integration so we don't have to go back. And so then b squared plus 3 is what's over here. And then x dx is du. The over 2 is out in front. X squared plus 3 is u. And then what we have here is the natural log. So then this becomes the limit as b goes off to infinity of 1/2 the natural log of u evaluated from 4 to b squared plus 3. And this then becomes the limit as b goes off to infinity of 1/2 the natural log of b squared plus 3 minus the natural log of 4. But as b goes off to positive infinity, this expression here goes off to infinity. And the natural log of numbers that get bigger and bigger goes off to infinity. And so then, therefore, diverges. And since the integral diverges, so does the series. So in our next problem, we have the series whose terms are generated by the formula n over n to the fourth plus 2n squared plus 1. Clearly the terms are positive. There's no opportunity for a negative number to come in here. Clearly the function is continuous because it's just a rational function, and there's the interval that we're looking in, there's no place for this to have a denominator of 0. But the only thing that's in question is, is it decreasing? I'm going to leave that for you. Just take the derivative and show that the derivative is negative. We've already done that on a couple of them. And so let's now just jump straight to the integral test. So for the integral test, again, we're going to take the limit as b goes off to infinity of the definite integral from 1 to b. Your lower limit of integration is always going to correspond to whatever number this is. That doesn't have to be 1. It could be 0. It could be 2. But whatever number that is, that's your lower limit of integration. And since it's infinity, then we're going to replace this with the limit as b goes off to infinity. Now here, if you are paying attention, you will notice that the denominator is a perfect square trinomial. And what it is it's n squared plus 1 squared. I'm sorry, I'm in the wrong variable, so let me fix that. Yeah, so the denominator is x squared plus 1 squared. You should recognize that as a perfect square trinomial. And so then again, we can do this with a u substitution. And so u will equal x squared plus 1, so that du is 2x dx. We have the x dx, so du over 2 is x dx. So then this becomes the limit as b goes off to infinity. We can exchange our limits of integrations. U is x squared plus 1, so we plug these numbers into this formula because these are x values. We want to make them u values. So 1 squared plus 1 is 2. And then b squared plus 1 is our top limit of integration following the formula. X dx we replace with du over 2. We'll bring the over 2 over here. And the x squared plus 1, we put u there. This integral is easier to evaluate if we rewrite it as the limit as b goes off to infinity of 1/2 definite integral from 2 to b squared plus 1, and u to the negative 2 is how that should be written. Just because you see a 1 over does not mean you have a natural log. It's only if it's just 1 over u. Now this is a power function, not the antiderivative. We use the power function rule. So we add 1 to the exponent and get u to the negative 1, multiplied by the reciprocal, which is multiplied by negative 1. We're still taking the limit. I didn't leave myself enough space. Let me pause this again. So again, what we're doing is taking the limit as b goes off to infinity. So I bring the 1/2 out. We have the limit as b goes off to infinity and then the antiderivative, we add 1 to the exponent, and so we get 1 over u, and multiply by the exponent, so we get a negative 1 out in front, and then we're going to evaluate that from 2 to b squared plus 1. So then this will equal 1/2 is just a constant. We can bring it outside. Take the limit as b goes off to infinity of 1 over b squared plus 1 minus 1/2. And so then this clearly goes to 0. And then the negative 1/2 times the negative 1/2 is a positive 1/4. It converges, and therefore both converge. Okay, so next, in our next example, we're going to start going over some very important types of series for us, because they're going to be very easy to identify, and they're going to be very easy to tell whether they converge or diverge. So show that the integral test applies and use it to test the convergence. We're not going to show that the integral test applies. Obviously, the sequence is positive. The terms are only positive. They're continuous. The function is continuous, and the terms are getting smaller, because as k gets bigger, the denominator gets bigger. So 1 over the denominator gets smaller. So 1 over that number gets smaller. Notice again that this can be rewritten using rational exponents as 1 over k to the 1/2. So these are the kinds of series that we're going to be looking at. 1 over k to a power. Now we're going to be able to apply the integral test, because it's going to apply to all these types of problems. And so then, to figure out whether this converges or diverges, we're going to find the definite integral from 1 to infinity of 1 over x to the 1/2 dx. And again, the way we do that is by replacing that with the limit as b goes off to infinity of the definite integral from 1 to b of x to the negative 1/2 dx. This is just a power function, and the rule for integrating a power function is to add 1 to the exponent. So we end up with an x to the positive 1/2, and we multiply by the reciprocal, 2. And then we're going to evaluate this from 1 to b. Substitute in the b, and we get the limit as b goes off to infinity of 2 times the b to the positive 1/2 minus, and when you plug in the 1, you will get a 2. But b to the 1/2, as your base gets bigger and bigger, the limit as b goes off to infinity, as your base gets bigger and bigger, this expression is just going off to infinity. And so then this goes off to infinity, and therefore your series diverges. For our next series, again, we still have 1 over k to a power, and in this case, the power is 3. We're going to do the same thing again, apply the integral test. We're not going to show that the integral test applies, it clearly does. So we're just going to start taking the limit as b goes off to infinity of the definite integral from 1 to b. And again, we're going to write our function, instead of 1 over x to the 3, we'll just write it as a power function, x to the negative 3 dx. Very basic antiderivative. So this becomes then the limit as b goes off to infinity we just add 1 to the exponent, x to the negative 2, divide by the exponent, negative 2, and evaluate this from 1 to b. So then again, this is going to be to pull out the negative 1/2, and we have the limit as b goes off to infinity of 1 over b squared minus, when you plug in 1, you get 1. But here, notice that what happened was, because my exponent was negative 2, when I added 1 to the exponent, instead of my factors staying in the numerator, they then went down to the denominator, and now the limit of this expression is 0. And so then here we get a positive 1/2. So if you go back and you look, in the last problem, our exponent was negative 1/2. Adding 1 to the exponent gave us a new exponent of positive 1/2. With that positive exponent, it stayed up on top, and the limit was infinite. But because this one, when we added 1 to the exponent, we still had an exponent of negative 2. Those factors went back to the bottom, and my limit, this term went to 0, and we ended up with a nice finite sum. And so you should think about, well, is there a deciding exponent where less than this exponent, you'll end up on the bottom and go to 0, or more than this exponent, you'll end up on the top and go to infinity, like the last problem. And we'll get there in just a little bit. Okay, so we're looking at these series where it's always 1 over the counter to the p power, and because it's 1 over the counter to the p power, these are called p series. We saw one where the p was 1/2, and when we tried to integrate it, it made it a negative 1/2. Added 1 to the exponent, and because we ended up with a positive exponent, that improper integral diverged. We saw one where the p was 3, and having that be a 3, when we rewrote it to integrate, it became a negative 3. Adding 1 to the exponent, it still stayed negative, and because it stayed negative, your limit then became 0. If n is 1, we could use the if p is 1, we could use the integral test as well. But earlier we saw that that's the harmonic series, and that then that series diverged. But it would be a lot easier to show diverged using the integral test than what we did earlier. But now we have this important result, and this is theorem 9.1.1, the convergence of a p-series. So if you have a p-series, and the limiting value, the determining value, is whether your p is bigger than 1 or your p is between 0 and 1. And if your p is bigger than 1, as we saw with the n cubed, then your series is going to converge. And if it's between 0 and 1, then when you rewrite it and add 1 to the exponent, then you will now have a positive exponent, and your series will diverge. If it's exactly equal to 1, then you can't use the power rule, but it's still the natural log, and the natural log increases without bound. And so we have this result. Not given a formal proof, but that's good enough right there. So in these problems here, it says use theorem 9.11 to determine the convergence or divergence of the p-series, right? So we just want to see this as a p-series, and then using whether our p is bigger than 1 or less than 1, just write down whether it converges or diverges rather than having to use the integral test. So when you look at this series, it's not 1 over n to the p power, so you might think that that matters with that 3 there. But because that 3 is a constant, because of our limit laws, this 3 can be taken out. And this 3 is not going to affect, this factor of 3 is not going to affect whether the series converges or diverges. So this is 3 times the series from n equals 1 to infinity of 1 over n to the 5/3. By writing it like this, now you do see that it's a p-series. You see that p is equal to 5/3. And then because it's greater than 1, therefore it converges. In this problem, we haven't been given the series in summation notation, so you need to write that in summation notation yourself. And so then again, we'll start with 1, k equals 1 to infinity. And then, except for this first term, notice that they all have a 1 in the numerator, and they're all fractions, and that they're all being cube rooted. But what's inside the cube root is not n. 2 squared. So here we have 2 squared, here we have 3 squared, here we have 4 squared, here we have 5 squared, and it even works for this one because there we have 1 squared. So what we have there is k squared. And so then again, using your algebra, we can rewrite this as the summation from k equals 1 to infinity of 1 over k, and taking the cube root of k squared is the same thing as taking k and raising it to the 2/3. The denominator tells you the index, the numerator tells you the power that's inside. And so then here you can see that this is a p series with p equaling 2/3, which is less than 1, and because it's less than 1, it diverges. Okay. So that is all for this section. Your homework is right there, 3 through 37 odd. I've uploaded the class notes, so be sure to fill out the class notes and stay on top of the class, do your homework, and we'll see when we see each other again. Bye.